Do you want me to share or?
So I think if Eka wants to share first, yeah. Eka, if you are ready.
Eka, you're muted.
Sorry, I was speaking here. Yeah. Yeah. So, is it okay now?
Yes.
Yeah.
Yes, I can see it.
Okay. Shall I start?
Yeah, if you want to just tell us go through chapter 6, and that would be great. Thank you.
Yeah. So we already covered like chapter, like topics such as like sampling methods and feature engineering, and the funniest part is coming now: model development and offline evaluation. And this chapter discusses how to select machine learning models that is more suitable for our tasks, and which aspects should be considered to make a decision for given objectives, constraints, and requirements. And also the chapter covers like different types of baselines and other evaluation techniques. So when considering what model to use, it's important not to consider just the model performance metrics, but also how much data we have, how much computer power, and how much time is needed to train the model, and how easy is it to interpret. For example, if we take like a simple logistic regression model, it might have lower accuracy and lower performance than like some complex neural network, but it requires less data, and it's easier to interpret, and it's faster to train as well, and easier to deploy. So there are like a few tips that we have to consider when we select model, make final decision which model. Yes. So the first tip is like we have to try to avoid the state-of-the-art trap. So what does it mean? Now, many people believe that the most recent and advanced model would be the best solution for our problems, but that's not always true. So if there is any cheaper and simpler way which can solve our problem, it's better to try this simpler solution. Yes. So and the second one, and yes, apart from the things that it's simpler models is easier to deploy we can use them like as a baselines as well. And it's easier to understand your model while your model is making some kind of this kind of predictions, and it's easier to debug. In addition, we have to take into account like some trade-offs we have to make. What this trade-offs means is that like we always have like none of the models are like of course perfect, so we have always like to this kind of trade-offs, and we have always to choose like the false positive against the false negatives. And of course we have to consider what type of task we have. Like if we have like screening, like patient screens related tasks, in this case like reducing false positive or reducing false negatives can be a problem. Yes. So we have to decide what based on what kind of task we have. We have to decide: is it better to reduce false positives, which will can lead to increasing false negatives, or vice versa? So in addition, we should take into account that the good model today does not always mean like good model tomorrow. Because like if we have like a tree-based model now which performs well, not bad, because we have few data, but after a few months, if our sample, if you have more data, much more data, like neural network can perform much better. And the simpler way, there's a way to estimate how models' performance might change over time. And this way is like using learning curves. On this slide, we have like results on like learning curves for different type of models. And it shows us that like adding some example on the training data can reduce or keep the same training score, but the important thing here is like that adding training examples, increasing training examples can lead to increasing like validation scores, which is much important. So yes, I will go next to the next slide. Yes, and of course we can like choose one model, but if you want to improve our performance, we can use not just one model, but we can use like ensemble of multiple models. So there are three ways of making this kind of ensemble. These are bagging, boosting, and stacking. So what does and ensemble methods are not useful, just not ensemble methods are useful, just not like improving performance, but they are useful for like when we work with imbalanced data sets, so which are quite common in real life. So the first type of ensemble methods are bagging, and bagging reduces variances, and it helps to helps to avoid overfitting. So how bagging works? We are given when we are given data set, instead of training one classifier on the data or on the entire data set, it samples with replacement and creates different samples, which are called bootstrapping. And the bootstraps, and the prediction are made like based on and yes, we train our classifier on these different bootstraps, and prediction is made combine these results. For example, if we have like classification problem, in this case, prediction prediction is related on. It takes the class which has more votes, and if we have like a regression problem, in this case it uses like average of each like training on these bootstraps. Another way of ensemble learning is like and the example of like bagging is a random forest. Another way of ensembling is like boosting, and it differs with bagging that during the boosting we use the same data set. We don't change data sets. We don't do like some replacements. But the thing is that like this is iterative iterative process, like iterative ensemble of algorithms. And the thing is that for each iteration, we weight data. We weight the data differently. For example, like we start like training the first classifier on the original data set, and then weights depend on this data set, and for the next iteration depends how well this the algorithm worked on this data set. And for each sample which was misclassified, it gives a higher weight. And for secondary iteration, it's like the algorithm will be trained on this reweighted data, and so on and so on. And by this way, the weak learners are converted to strong ones. And another method of is one more method is stacking. And in this case, we have like base learners, which are trained them from the training data, and the output is like combination of each predictions. So majority weight again is like for regression is again the average, as for final prediction is of average of these predictions. And for classification tasks, the major is like class is given by the majority of weights. So yes, the next topic, next thing discussed in this topic is automation learning. And automation machine learning is a process of finding machine learning algorithms to solve real world problems. And it discusses the importance of hyperparameter tuning. We know that the goal of hyperparameter tuning is to find the optimal set of hyperparameters for our given model. So, and in the book, it mentions that sometimes and quite often, like weak learners and simple models, which are well tuned, so with hyperparameters, can overperform some fancier models as well. So, and like the book discussed as well in the chapter architecture switch and learned optimizer, which is used in deep learning neural network.
Eka, I'm just going to say, so if you're able to just finish this section quickly and maybe do the key points of the chapter. Okay. We do have quite a few chapters to get through. Yeah.
Okay. Okay. Sorry. So okay. So I thought I am quite stuck. Yes, so the chapter discusses as well some different offline evaluation and why machine learning will run some baseline methods and evaluation methods as well, like permutation, invariance test, and yes, I won't stop. So key points from the chapter, it's like we have to focus on a set of models which is suitable for a given problem, our problem, and simple machine learning models are easier to implement, deploy, and interpret. And ensembles reduces the variance and helps to avoid overfitting. And choose the best set of reference on a validation set is important. And we don't have to and the report models perform on the test split. And so we have to choose the hyperparameters. We have to choose the parameters based on the validation test, and we don't have to use like test split test set when we are choosing the hyperparameter. It's the crucial. And sensitive information should be excluded from the features during training models. Sensitive information such as gender or race it should be excluded from the training model. And what I liked the most about this like chapter is like not the chapter in this book, like it gives some like information about some different like some different machine learning conferences. And I like it was interesting because I just watched some of this like they are available on YouTube as well, so it's good to know. So sorry if I was too long.
That's right. Yeah, no, thank you for that summary of chapter 6. Yeah, I'll pass it over to Sahana then. Sahana, are you okay to share your screen?
Yeah.
Amazing.
Awesome. Thank you so much, Hector. I'll get started. I'm Sahana. I'm going to speak about model deployment and prediction service chapter. So earlier on, we basically went over how to curate a training data set, like create features through feature engineering for the models, feed it to the model for training, and also like how do we evaluate these now trained models using metrics. So the author terms all of these steps as like ML application logic. So this chapter basically focuses on like moving this logic to production. Deployment basically means making your models accessible. So one might ask, like, then where does all the other things happen? Well, I can basically say that whenever you're like improving or like training the model, it basically happens in the development environment. And depending on the companies we are talking about, some companies basically move directly to production environment, and some companies have like a staging environment in between where the models are tested before they are promoted to production environment. And also another thing we need to be aware of is like production. When I say production, it's a very big spectrum. It can basically mean like creating some plots to share with your business team, or it can actually mean like serving your model or deploying your model in a place where it's accessed by millions of users. So now let's actually basically talk about model prediction and the infrastructure. So why the author basically makes a very important point that regardless of whether in our current role that we do deployment or not, being aware of it always helps. So before I basically talk about model prediction, let me take a step back and kind of just clarify what does prediction means. The output that's created by the model is basically called predictions. This entire process of model creating output is called inference. So the author originally basically says that there are two different ways a model can serve or generate predictions. First is an online prediction, where the outputs of the model are served in like real time. And second is batch predictions, where the model basically is fed like a group of inputs, and then it computes basically output to each of the inputs, and those are served to the users. And also there's another classification that's happening here. Based on where the model computes the predictions, it can be like an on-edge computation, where where the model predictions happens on the devices, like imagine your mobiles or watches, etc., or cloud-based predictions. And I also like wanted to share like a very hard-hitting line for me, and I'm going to read it out and then like share some examples of like to basically help us appreciate how beautiful it is. Like the author basically says that how the model serves and computes the prediction basically will influence how it should be designed, the infrastructure it requires, and the behavior the users would encounter. So I have like two examples for us, like to appreciate this line better. Let's take an example of like Netflix recommendation systems. Here, Netflix basically makes predictions in batch, and they are computed offline and cloud. How does the model should be designed? Well, because the predictions are like generated in batch, accuracy is more important here, not latency. Like model can take a lot of time to give out results, but it needs to be highly accurate so that the users are interested to use the service. Infrastructure constraint. What is the infrastructure constraint for a system like this? It should be able to handle like large amount of data, and hence will have like a high memory requirement usually. What is the user experience? Because these are like batch predictions, the recommendations are ready to be shown as soon as the users log in. Let's go through another example like this. Uber's pricing models. Here, the predictions are served online to calculate like the prices in real time. What is the constraint on the model? Model has to be low latency. The predictions should be shown to us really fast. Infrastructure constraint. Millions of people use Uber every day for like book their rides. So it should scale horizontally, and it should be able to scale to handle so many user requests simultaneously. And finally, what is the user experience? Here, the users get instant price quotes when they request a ride. Fascinating, right? Like now the author tries to like debunk some of the myths of the model deployment for us. The first myth the author debunks is like you will deploy only 1 or 2 models at a time. So like going back to the Uber's example, like all of us know that when we use our Uber app, there are like multiple features that are like basically being predicted for us. Like for example, the driver availability, estimated time of arrival, the dynamic pricing, etc. So these are like couple of the, so clearly there are like multiple features that are being used in the system. Also, if you think about it, like if Uber is like active in more than 20 countries. So given that we don't have a general model everywhere, there would be a model for each of these countries. So clearly this point is wrong. If we don't do anything, the second point, if we don't do anything, the model performance remains the same. Well, Ekta basically shared in the previous section that like the model good today might not be good tomorrow. Well, that's basically is a guiding force of a lot of companies out there. The model's predictions might be good, maybe close to its training times after it's being deployed, but it's very important to like basically monitor the performance so that when it degrades, we can replace it. And the third point that author debunks is that you won't need to like update your model as much. She basically challenges us saying that we should not ask the question, how often should I update the model? Rather, we should ask the question, how often can I update the model? And and there's also like a couple of very interesting facts that are shared. Like Etsy, for example, deploys model 50 times per day. Netflix, thousands times per day, and AWS is deploying a model every 11 seconds. And finally, the last point, like most of the ML engineers don't need to worry about scale. This is also a very, the way the author debunks is quite interesting. While it's true, there's only like one Uber, one Facebook, one Google. The Stack Overflow developer survey of 2019 apparently says that more than 50% of like software developers work for at least 100 work for companies that have at least 100 employees. While there isn't a perfect correlation, a company of 100 employees might have it's reasonable to say that they might be serving like a reasonable number of users. Therefore, they need to think about scale. And so basically the author ends this argument saying that, yeah, as an ML engineer, we always should have scale in back of our mind. So moving on, like I'm again going to like take us back to the predictions and infrastructure. So here I shared earlier the batch predictions means that you're making predictions based on like batch features. Online prediction means that the model is basically making predictions based on batch features, but in real time. And finally, there's a separate entity called online prediction streaming, where the model is not just making predictions based on batch features, but it's also making features on like some of the real-time input as well. For example, an example of a streaming use case could be like a fraudulent transaction. Like it needs a couple of data. It needs is like not just a transaction at the moment, but also like what are the transactions the user has done in the past, so that like a particular transaction can be flagged as fraudulent or not. And before I move on to the next slide, I just want to make the one very strong point that the author makes. No matter what we choose, it's very important to make sure that we use the same pipeline both in training and inference, so that we automatically do not end up feeding like different different features to the model, like something different in training and something different in inference, and such thing might lead to like wrong results. And the next point that the author makes is about the model compression. So model compression here is a wide umbrella that also doesn't mean like reducing the model size, but also like making models make faster predictions. Having a real-time pipeline is not fast enough. We also need faster models. And the process of making models to do inference faster is called inference optimization. There were like a couple of examples of model compression that was shared in the book. The first one was like low rank optimization. Initially, earlier on, they had like a one standard convolutional filter that was responsible for learning both spatial features in the data and also the channel interactions. Later on, that they found that instead of using like one feature to do everything, if they can split the job between like a depth-wise convolution that's responsible for learning spatial and point-wise convolution that's responsible for learning channel interaction, it overall leads to like lesser computation and therefore faster model. There's also another technique under model compression that was discussed, which was knowledge distillation. This basically means they teaching big models teaching small models, like a teacher-student relationship. And it was interesting. One of the interesting facts that was shared in the book was the distal BART, which learned from the big BART, was 40% smaller, but it was 60% faster and had 97% similar performance as the bigger one. The third one that was discussed was pruning. Pruning, we might have heard it in like decision trees world, where it's basically just like removing some parts and etc. It's a very similar concept here too. It means like removing some nodes in the model, or it could also mean like setting some of the parameters to 0, thereby making the model sparse and thereby helping it in like compressing it, thereby helping it in compression in the later stages. Finally, there's a fourth and important method that was discussed under model compression, quantization. This is by far a lot more commonly used in inference. So how this happens is basically the model parameters are by default are coded in 32-bit. Instead of like using 32 bits in inference, we use 16-bit, and thereby making the computation faster and also the model size smaller. But however, one of the most important things to take away from this is that we also have to make sure that model compression might lead to some performance degradation. So it's basically it's on the responsibility of the developers to make sure that we are not compromising too much, and there's a kind of a trade-off equation here. A last point before I hand off. One thing I did not discuss in detail here is like the final portion of this particular chapter that talks about like ML on edge and ML on cloud. ML on edge cloud is clearly more talked about, like and a lot of resources are out there on like AWS, GCP to educate us more about like how to run the models on the cloud. And a lot of these systems have been made easy because they want developers to jump in as fast as possible. But the author also says that the ML on edge is a very interesting part too, and it also requires equal attention, because this could be the space where like users have like more control, and it's also like little more challenging than the cloud. So yeah, definitely something to read more about and pay attention to. That's all I have. I'll stop sharing. Please do drop questions if you have in the chat.
Yeah, thanks, Sahana. That was really great. I think we'll just go right straight over to Ying because we're a little short on time. Ying, if you're okay to share.
Sorry, I was muted. Yeah, so thank you. So can everyone see my screen? So, okay, so basically, the chapter I'm going to talk about is right after deployment. So once the model has been deployed on the system, like a Netflix or Uber, when they start to update their system or start to put a machine learning model into it, the moment they add this model online and start to do the prediction, the quality drops immediately. The best quality is when they start deploy this model, and then they were going to suffer a lot of things like data distribution shifts and also problems, and also maybe some major event happening. Maybe there is like a Heathrow airport shutdown suddenly. So all these, all the, I would say, input features start to changes. Like suddenly the price going to Heathrow is probably dropping to, I don't know, very little. So there are so many things. These are very important in production side. So we are talking about the system failure. We call them system failure in software engineer and in both machine learning engineering part. So this failure would involve in operational matrix start to drop, like the inference time could be like become from 1 second or 1 millisecond goes to like 10 seconds, and could be a performance matrix failure. It's like the accuracy starts to drop, or the prediction start to, or even though the accuracy remains the same, maybe somehow my true positive and then true positive and false positive start to kind of messed up. So to understand what type of failure it is, it's quite important. The part with software failure is that it is something observable. You can think about it as a bug. Like if you are running your, like, let's say if you are having an app like Netflix, and suddenly like this whole app froze, or suddenly it doesn't show any movies anymore. It doesn't recommend you anything anymore. You noticed it. It's a software failure. But what happens is more, I'll say, dangerous would be a machine learning specific failure. They are silent failure. If your accuracy, let's say, if your accuracy drops from 90 to 50%, you will notice, the user will notice. They'll be like, okay, suddenly Netflix doesn't recommend me the movie I wanted to see. The Uber starts to give me like a price of like £30 to go from King's Cross to Euston. That's outrageous, right? It's more like a silent failure. Or if the price goes, well, I would say, well, £30 to go from King's Cross to Euston might be a little bit way too obvious, but it would be something like just I think a while ago, like last year, there is Air Canada was basically having this chatbot, and they started giving out this fake discount and trick people into buying their tickets somehow. I don't think it's intended, but this is definitely one of the very obvious silent failure we observe in machine learning, especially in large language model. So actually, to talk about what type of failure it show up, like we can go to 3 parts: data distribution shift, edge cases, and degenerate feedback loop. I'm going to talk about feedback loop first. So what is a feedback loop? It's also very common in the recommendation system. What happened is like if we're recommending an item to our user, the recommendation algorithms are largely affected by the popularity of this item. Let's say if you are on Netflix, you are watching movie, you get recommended by I don't know Marvel's movie, let's say. So because Marvel's movie is so popular, if it show up on the internet, it will be very obviously like get on top of your list, and you will start to click on it. The thing is, the prediction results would affect your user behavior as well. What happens is that the algorithm noticed the Marvel's movie is very popular and put it on the top of the list. And you will scroll down probably like 2 swipes on your phone or 2 swipes on your TV, and then you choose probably Marvel's movie because it's so popular. Then this knowledge will be get feedback to back to the algorithm. Then slowly we'll get this. We think because popular items start to become more and more popular, and the items which are less popular start to vanish in your list because they never got chosen. So it becomes like less likely to be clicked and less likely to be recommended. This is degenerate feedback loop. So how do we actually find it? Like, how do we observe it? Because you won't even know when it happens. So something I want to talk about is the popularity diversity. In general, popularity is actually follow a long tail distribution, which is shown in the right side. If you are putting popular items based on the popularity, you will see that there will be a large amount of clicks, or we call it clicks. Like if you are seeing an item and you click through it. So this is how the companies actually collect the information about them. So like they say, okay, people click them, so it's counted as a good recommendation. Then you have this long tail distribution. So by observing this long tail distribution, you from the evaluation, you will see that okay, generally the evaluation, the accuracy on the popular item are higher than the less popular item because they have more data, they have more user interaction, and then of course the evaluation, the accuracy becomes higher. This is because of popularity bias, but this is also the reality of the model. It's not a degenerate feedback loop yet. But along with time, you will notice that when you start training it more and more with probably when we have data from, let's say, the previous year, and then we start to introduce new data to actually train it, you will start to notice that the accuracy among each popularity bin item. So based on if items are separated by their popularity and test the accuracy upon them, you'll notice that they start to become similar. And this is when the degenerate feedback loop are happening. How do we actually correct it? We could do a randomization. So let's say we don't just recommend the items generated from the algorithm. We are throwing in some other items, like which are not really on the top of the priority list or the recommendation list. In this way, we can start to correct our algorithm slowly, or we can put a positional feature. We can say, okay, this is top of the recommendation list. It can be a binary way saying that, okay, 1 and 0 or true and false to say that, okay, this is actually very popular. Or you can put basically a ranking score, and this will give the algorithm a knowledge of, okay, there is a positional feature. Or you can mix them up. You can start to say, okay, I put a positional feature. I also generate using a model to actually predict the recommendation without the positional feature, and we are going to do a weight, like a model ensemble, like I mentioned, or different ways of mixing them to make sure there is some knowledge of the position, but sometimes there isn't knowledge of the position. So in this case, we can start to promote some less popular items. In this way, it will give a more reasonable, it won't actually tune towards the popular item, as well as also keep the, I would say, the maintain the user experience, because if you're throwing some less popular items, maybe the users start to stop using the app or the software. So another thing is data distribution shift is also another reason to cause the cause the failure, machine learning failure. I'm not going to go deeper into the shifts like covariance shift, label shift, and concept shift. Think about it as input shift. Your input data start to have a different distribution, your label start to have a different distribution, and also your algorithms start to have the way how the input and output start to connect to each other start to have a bit of change. How to actually detect the shift? There are statistical methods. I have a list of these statistical methods, and I think it will be too much to actually memorize all that. They are all in the books if you want to actually look into this. And also there are time scale windows to detect the shift, because some of the changes of the input data or feature shift or label distribution could be caused periodically. Such as a hot season. So something like if you're selling an item, maybe you are selling more on weekends instead of weekdays because people are really busy over the weekdays doing their work. So the time to decide the time scale is quite important. So you can include the seasonal shift, which is reasonable in the data distribution shift, or if you are including something within half year and you notice some shift which is not supposed to be there, and slowly it's not like the whole data is not stationary, which means that not actually fluctuate around a mean value, it starts to actually shift upwards, like the house price start to slowly shift up. This is something which will change slowly with time. So actually, how to address the shift? Okay, sorry, it's not actually mentioned here. So how do we actually address these shifts? So you have a model and you have input data shifts and output data shift or some logic shifts. So how do we actually solve it? Retraining. Or retraining is something which is going to be we are talking about, okay, train with loads of data, like with the whole data, like the whole data set. So hoping it will actually capture this shift. But more frequently, we are talking about fine-tuning, which is a more familiar term, fine-tuning or transfer learning, or something, or distillation is also could be used in this case as well. So something we are using new data to tune our models into a direction which actually adapts to the newer data distribution. Then, so in the end, I want to talk about system monitoring observability, because this is quite important. It's also, I think it's also showing up in a lot of machine learning system design interviews, because you want to monitor this system to make sure that, okay, I noticed this data distribution shift. I noticed that there is failure in my machine learning model, my performance is dropping. There's so many things to look at. So from machine learning point of view, there are 4 things you can monitor. You can monitor the raw input, you can monitor the feature, you can monitor the prediction result, you can monitor the matrix. Like these are the 4 main bits you can monitor. The thing is, think about the matrix. If you are having a recommendation system, you can monitor what is my click-through rate compared with my evaluation matrix from the model. Is it going further and further away? That's easy to predict. That's easy to monitor. But if I'm talking about the raw input, then we're thinking about, oh, there's I could have 100 inputs for a sample. Then can I actually monitor 100 of them? And how do I monitor if I'm having a different age group or something which is easy to see in a distribution, or I have something which is easy to see in a category? There are so many things to monitor. It gets harder and harder. So which means it's easy to monitor metrics, less easy with prediction. And when it gets to feature and raw input, it gets harder and harder. So you need to decide what can you monitor and what do you want to monitor to make sure you can balance between the computing efficiency and easy to observe that kind of things. So to be able to monitor that, because the machine learning model are running constantly, or they're running in the cloud, so we need to have logs. It would be nice to log everything. Then you have a piles of data set of log. You can even look at if I monitor some, like let's say my metric is shifting, then I can go back to my log, and I don't know when it happened. I don't know how it happened, or I don't know which part went wrong. So you can look at this. The thing is, like, someone would even, some company would actually design a RAG system, which is like a large language model system, to actually to find out where the problem goes wrong. You can basically retrieve information from your logs. And also you can observe it from dashboard. You can observe in curves, or making some distribution to show, okay, I can observe distribution shifted from like last month. And you can also set up alerts to send you a message, send you an email saying that, okay, I'm monitoring these metrics and they are changing, like let's say 50, changing by a large amount. It's into a dangerous level. Maybe it's time to consider updating your model or do something else. Monitoring is a part, but another concept which being introduced is observability, which means when you are monitoring things, you are just looking at some part you want to look at, but in reality, you need to keep everything available. You need to, like, each step, you need to have a log. You need to offer this information for people to look for them when they monitor it. So think about a log. If you have like 100 or 100 million lines of logs for the system, when you monitor, you'll probably monitor like, I don't know, like 5,000 of them, but the majority of it need to be offered the observability for you to see it. So this is the system monitoring observability. And then I'll pass it to Nino to talk about continuous learning and testing production.
Thank you. I will share my screen, okay?
Yeah.
Yeah, this one. You see my screen, right? And you hear my voice?
Yes.
Yeah, amazing. Thank you. Okay, so I will try to walk you through how to make our machine learning models useful over a large period of time. So the key topics we will cover in this chapter 9 will be, first, continual learning, which is how to stay relevant by updating our model periodically. The second will be model update strategies, because there is two. The third one will be the challenges of continual learning we will encounter. And once we choose our model, then the last part will be about testing before we put our model in the production. So let's start with the continual learning. Let's take an example that we have our fraud detection model that we trained in 2023, and we are now in 2025. So if we have our static model, which on the graph is the red dotted line, we see that over some period of time, model performance degrades and drops. However, if we chose continual learning strategy, which means that our built model learns from new data over time without forgetting previously learned knowledge, we see that model performance over a period of time is much better compared to the static model. Let's move now to the update strategies. As I mentioned before, we have two of them. One is stateless and stateful. Let's start with the stateless one. It means that every time we train new model, it's built from scratch. So from zero, no history, no anything. We start from zero. While stateful training means that we have our model built once And once we have gathered new data, we add the new data and improve the alteration of the model. For instance, let's take an example because it's always much easier to understand. Stateless retraining would be that we have loan approval model, which we train quarterly, and we take all the approvals and rejections of all the history, all the previous years we have, and we train the model. While stateful training would be that we have card fraud detection model, and after a day, when we have gathered transactional data, we add this transactional data and we do the updating model stuff. So every day we have some data and or several days and we update the existing model. Now let's move to the type of model updates. We have model iteration or data iteration. Let's look at the model iteration. What does it mean? For example, if we want to add features or reduce features or just change hyperparameters of the previous model, or we want to change an algorithm. We had a decision tree before, and now we see that we need more complex algorithm, and we choose XGBoost. It means that we are choosing model iteration strategy. While in case of data iteration, we don't take anything about them. We don't change anything about the model. Everything stays the same, and we just add the new data, and we do retraining in this way. So this is called data iteration method. Let's do quick summary. Why continual learning? We said that it's better. We saw on the graph that model performance is much higher, but let's do the quick 3 points, which will exactly show us. First one is handling data distribution shifts. Let's take an example, for example, Uber or Bolt or any taxi driving app that every day it works fine, the model we have trained for. But if there are some occasional situations, for example, concerts or sport games or competitions, when the situation changes and demand of customers suddenly increases, our static model won't be able to see these updates, while with the continual learning, the prices will be updated dynamically and there will be enough drivers to meet the supply to the demand of the customers. Another reason would be adapting to rapid events. If we take again our example of fraud detection model, if we trained fraud detection model in 2023, but in 2024, fraudsters have new strategies, and this is not seen in the static model, it will degrade. But if we update occasionally, it will catch the new strategies and it will identify fraud transactions better. And the third one is about improving personalized recommendations. And in this thing, I think TikTok algorithm shines. For instance, if you have a cat and you go on TikTok and you watch and scroll cat videos, but after several days, you are interested in dogs and you watch them, the next day, it will dynamically update. It will learn your preferences within minutes, and it will update in a way that it will be really fast, unlike traditional batch learning, which takes days, weeks, or even months to update. And so you suffer with delayed personalization if you are a user of it. We mentioned the benefits and advantages, but everything has its own challenges, and so has the continual learning. First one is that accessing real-time data is difficult because some companies today still rely on data warehouses, and getting up-to-date data can be slow. So in case if you want to use real-time data, you need data streams from platforms like Kafka, which needs its own structure and infrastructure to be built, so it takes time and it's not easy. The second one is that we need frequent evaluation, because if every day we get new data and we have to retrain our model, we have to also evaluate that our model is not biased. And the third one is that some models can't do continual learning. For instance, neural networks adapt to continual learning. But if we take tree-based methods, XGBoost, random forest, no matter, they require retraining from scratch. So if you are using those algorithms, you can't use continual learning method. Right. So we have, up to this point, we have chosen our model, strategy, we have built and chosen the best model, and we are ready to put it into production. But before we put it into production, we have to test them. And there are several testing strategies. Let's start with shadow and canary deployment. What is shadow deployment? Shadow deployment means that your new model is deployed aside the old model, but it's only used for validation. Like you validate, you see the model metrics, how it works technically, but you do not make decisions based on the new model. You make decisions based on the old model 100% of the times. While canary deployment, in real case, like 10% of the real users are done with the new model. Like you really use the new model on the real users, but only on certain percentage of users. And after you evaluate and validate and you see that prediction responses are fine and they are exactly what you were looking for, then you increase this 10% and you will finally go to 100%, so full deployment on the using the new model. Another testing strategy is A/B testing. I think it's well known, and as the name suggests, it's like we have two groups, A and B. Group A is shown model A metrics, and on the group B we use model B. And finally, we look at retention or streaming or click-through rate or watch time. And based on the metric, whatever we have from the business, we evaluate which model was best one, and we leave the model which will have higher metrics. Compared to A/B testing, is multi-armed bandits, which is superior than the A/B testing, because in terms of A/B testing, we have traffic allocation fixed, but we evaluate the model in the end. So we wait everything to finish and then evaluate the model, while using multi-armed bandit simultaneously, like it identifies the best option, best model, and then allocates the traffic to the best model, so it's dynamic more, and it doesn't wait for the finish line to evaluate. It will do this automatically. Yeah, we finished the testing methods in the production, and with this, we also finished the chapter 9, and we move to chapter 10. Yeah, I will continue again. So, and we go to infrastructure. This is very important topic because it's great to have trained model, to have code, but if we don't have right infrastructure for our MLOps, we won't last long in the production. So we have 4 main layers. We have lowest layer, which starts from storage and compute layer. And we end up to the top layer, which is development environment. We are data scientists, so we work every day. Let's start with storage and compute layer. So this layer provides a raw compute power, like storage to run experiments, to store data sets and serve models. Next comes resource management, which like schedules and manage tasks. ML platform is like central hub, which has everything that needs for training, evaluating, and deploying models, and development environment, which is used for daily writing code, Git, Jupyter notebooks, VS Codes, and CI/CD pipelines. Let's go and deep dive through each layers. We start with storage and compute. On the graph, we see the comparison of enterprise spending, how it changed over the last decade. The blue bars represent spending on traditional data centers, like the companies buying their own physical servers, while the orange color shows spending on cloud infrastructure services when companies went computing power. And we see definitely that after 2019, it has really increased, and we are now in 2025, and you can imagine how this gap has even increased. Let's move to resource management, our second layer. Here, this resource management is used to kind of take our code and connect to the machine where it has to be run on. Let's take such example that you are a data scientist and you have your job stages, like you load data, you train a model, you evaluate and save the metric. So you have 4 stages. These 4 stages are translated into 4 tasks, but these tasks have their own order that they have to be executed on, and their time interval. There should be difference between each task when it's executed. For that, we use schedulers. Schedulers like Apache Airflow. After schedulers, there comes the role of orchestrators like Kubernetes, which allocates compute resources and runs tasks on the right infrastructure. That's the role of the Kubernetes. And then comes the last part, is the instance pool, which is for executing ML workloads. ML platform. As you see, it contains 3 main parts: feature store, model development, and model store. We start with feature store. This is centralized feature system which helps that data scientists do not engineer the same features over and over again. And these features are saved and calculated in feature store, and every time each data scientist can directly use them. Next is the model development part, where data scientists test several models, use hyperparameters, debugs, and everything. And once they chosen and validated models, they are finally saved in the model store. So several models are saved in the model store. And the last and the top layer of our infrastructure is the development environment, where mostly data scientists spend their time on. So it contains first an integrated development environment like Jupyter Notebooks, as I mentioned, VS Code, PyCharm, which provide tools for writing, debugging, and running ML code. Versioning is crucial for tracking changes in data and code. In terms of tracking changes in code, Git is very useful, and for changes in data, DVC. And CI/CD is continuous integration and deployment, which automates testing and deployment. From my point of view, if you're a beginner in data science, my advice would be that pay much attention to use integrated development environment like VS Code or PyCharm rather than Jupyter Notebooks, because in the beginning, I started using notebooks, Colab or Jupyter Notebook, and it took me really a great time to kind of switch to VS Code, because in VS Code and PyCharm, you have folders separately for training, testing, inference dataset, and everything. You allocate resources exactly as it needs to be done, and you have clearer codes and style, and it's always better to start writing like that rather than like me and then have problem to switch to the correct version of coding. Yeah, that's how I will finish chapter 10, and yeah, it was all from me.
Thank you so much, Nina. I think it's Sahana doing our very last chapter.
Hi again. This chapter is the human side of machine learning. It's also like the one of the smallest chapter in the book, and it's definitely a good read. So the human side of machine learning, the author basically says that it involves the users as well as the developers, and slowly will reveal like what are the different things that come under users and developers. The first thing is like the user experience. So like one of the things about like ML systems is that they are probabilistic, and one of the few things as users look out when they use an app is consistency. So you can imagine like when we basically give the same prompt to ChatGPT, we get different outputs. And imagine like building a downstream system on behind this, because if you have like if you basically have like some sort of component that needs a constant output structure, and if you have a component before it that is quite random in like in creating the outputs, it can basically mess up the experience, and it could lead to like situations where things are not consistent. One of the examples that's quoted in the book is an experiment booking system booking.com did. So basically they had like 200 filters at one time, and they deployed a model that basically suggests a user like 10 or 15 filters based on some sort of features. And what happened was that like sometimes a user really liked a feature, next time they wanted to use the same feature, it doesn't come up for them. This they learned it the hard way, that the users who use their platform are indeed looking out for a consistent experience. This brings the second point in. Sometimes it's very hard. It gets really hard to say which is the right output to share to the user. The author basically says that maybe a right approach to use here is basically share multiple predictions for the same input, and let the user decide which is the right for them. And the last thing is basically something called smooth failing. Failing here is not exactly fully negative. So what happens is that like we do a lot of we went through like how to increase the like basically have a better experience for the users by like using a model that has low latency, etc. But there could be some points in the actual production where the model is basically given such an input where it takes a lot of time to generate an output. In this case, the author says that in such a situations, different companies have different ways to tackle them. Some companies have like a two model approach where they basically have an if condition. If the main model takes a lot of time to predict, switch gears and use the second model. Sometimes the second model could be a very simpler solution. For example, like if the main model takes a lot of time to generate a prediction, just use the pre-computed prediction for a similar input. The basically coming back to the human side of machine learning for the developers, the author basically takes a chance here to talk about like how does a team structure should look like in a company to bring ML ideas to life. First, I'll start with the approach to basically expecting a data scientist to do everything from like managing the infrastructure, with Nino just went over earlier, to like training models, curating the data set, trying to figure out the right problems they want to solve is a lot to expect from a single position. So rather it's better to have like a cross team collaboration where right skills are used to drive the product forward. Here, the author makes a case that the subject matter experts should be involved in the project planning and should be involved in like creating the problem statement, which will increase the success criteria, which will increase the success of this particular project, for example. And it's also important that the subject matter experts are involved in like labeling the data. A lot of times, a lot of the models that are released are not like, it's not a permanent release like we went over earlier. The models have to be like retrained and to make sure that they're keeping up with the data. In these situations also, it's very important for the subject matter experts to be involved. And finally, there was actually also another interesting point that was made in the book about a particular technique which the Netflix follows. It's when like basically a lot of ML projects need a lot of infrastructure component to it. So most of these projects apparently start with like people with the right skill set to set up the infrastructure, and slowly they themselves write code to replace them, so that the data scientists who sit on them can use the tools they built and not depend on not need to work with an actual person to bring their ideas to life. And also another thing that's talked about in this chapter is responsible AI. Responsible AI needs no introduction, but I really love how the author basically uses two examples of irresponsible AI to help us understand why we should be thinking about it. There was like two examples. The first example is basically in the summer of 2020 when UK had to cancel A-level exams because of COVID pandemic. The solution of PAL, I assume, came up with was basically let's do this. Let's combine the previous data for each school, and also like the teacher assessment which is given to the students in this current year, and basically use a statistical model to predict what score the student would get. The problem is like they made a lot of biases, and it created an issue much later. The first issue was that the OFPAL basically assumed they just evaluated saying that their model has like a 60% average accuracy across the A-level subjects. This is basically what a regular examiner would have as well. But this is not enough for a model that's going to impact the futures of so many students. They, in fact, were so focused on making sure that the fairness is maintained between schools. They did not focus on the right objective, which was basically to ensure that each student gets a fair grade. And also, the evaluation they did was not like fine-grained enough. They let a lot of biases skip through. For example, if a student from a low performing school is actually smart, he or she would be given a lower grade, and that's a pretty big problem. Similarly, the teachers in some school might be biased against certain races, and they might give lower grades to like already marginalized communities. This also might like lead to a lower grade to that student. This is actually a very good example of irresponsible AI in my opinion, and it basically brings a strong point that systems like this should not be developed in darkness. It should have like a representations from like different skill set, like policy makers and subject matter experts, to make sure the right system is delivered. The another example of irresponsible AI that was discussed was basically an example from Strava. Strava did something really cool. They released 1 billion activities between 2015 and 2017, tracking around like 27 billion kilometers. They wanted to like release the data in good faith to help the developers to develop something cool. What ended up happening is that like sometimes the activities of like Strava users who also happen to be military personnel in like areas like Afghanistan, Russian patrol area of Syria, I guess, were exposed. And some analysts claim that you can also extract like users' personal data from this. This is also an example of when before like releasing a feature, like you should actually think about the consequences and make sure like things are protected enough. And one of the things that one of the features of Strava had initially was that as a user you have to opt out, or basically in other way that you need to like opt into privacy settings. But by default, your data would be can be shared. That was like the default setting. So sometimes the developers need to like think of themselves in the shoes of the users, and who might not be as technically advanced or like technically thinkers like them, and make the right choices so that the catastrophic incidences like this will not happen. Finally, the last thing I want to talk about is like a framework for responsible AI. There are like few different frameworks that was discussed. The first one, biases can happen through multiple points in the model lifecycle. It could be through training data labeling. It's very important to have to make sure that you follow the right practices and right testing so that the model biases are caught earlier. You need to also understand the limitations of the data-driven approaches. Models are basically learned from their training data, and it is possible the training data cannot cover all of this in all of the situations out in the world. There might be a low represented data. So if you have to make sure that you are doing enough thing to cover that case as well. It's also important to act early. Create model cards. Model cards here means like basically what is the training data of the model, how did you evaluate it, what is basically the model about, like basically share as much as you can about the model, especially if the model is going to like impact public or like millions of users, for example. And finally, basically, I'm going to end this by saying that it's also very, very important, because responsible AI being an evolving topic, to stay up to date on what's happening out there. And that's all I had. Thank you so much for like tuning in.
Yeah, that was great. Thank you. And yeah, that last chapter I think also is so important. You know, thinking about all of these technical aspects, and it's important to remember, you know, what does this mean for all of our users? Yeah, so no, honestly, thank you, Sahana. Thank you as well to Ying. Thank you to Eka. Thank you to Nina. Yeah, no, honestly, thank you to all of the volunteers, Prabha as well, who's co-host. And yeah, I think we're out of time for tonight. But if anyone has any questions, yeah, I would say just reach out on Slack, reach out on LinkedIn. Yeah.
Thank you, everyone. It's a great session.
Thank you,
I hope you
everyone.
enjoyed it. Thank you.
Yeah.
Bye. Have a good evening.
Yeah.